electrical safety relies heavily on grounding and bonding. These two concepts, while often used together, serve distinct purposes in protecting people and property from electrical hazards. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers to trip and de-energize the circuit. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same potential, minimizing the risk of electric shock. Let's delve into grounding first. The primary purpose of grounding is to provide a low impedance path for fault current. This path allows a large amount of current to flow quickly back to the source in the event of a ground fault. A ground fault occurs when an ungrounded conductor, often referred to as a hot wire, comes into contact with a grounded metal enclosure or any other grounded surface. Without a proper grounding system, this fault current might not be high enough to trip a circuit breaker or blow a fuse. This could leave the metal enclosure energized, posing a significant shock hazard. The grounding system consists of several components. Firstly, there's the grounding electrode conductor, which connects the grounded conductor, typically the neutral, at the service equipment to a grounding electrode. The grounding electrode is a buried metal object, such as a ground rod, a ground plate, or a metal water pipe that is in direct contact with the earth for at least 10 feet, providing a connection to the earth. Secondly, there's the equipment grounding conductor, which runs with the circuit conductors and connects the metal enclosures of electrical equipment back to the grounding bus at the service equipment. This ensures that all metal parts are effectively grounded. The National Electrical Code, or NEC, provides detailed requirements for grounding systems. For example, NEC Section 250.52 specifies acceptable grounding electrodes, and Section 250.66 outlines the required size of the grounding electrode conductor based on the size of the service entrance conductors. Ensuring compliance with these codes is crucial for a safe and effective grounding system. Now let's move on to bonding. Bonding is the practice of connecting all metallic parts of an electrical system together to create an electrically conductive path. This includes metal conduits, metal enclosures, metal water pipes, and any other metal parts that could potentially become energized. The goal of bonding is to ensure that all these metal parts are at the same electrical potential. If a fault occurs and one of these metal parts becomes energized, the bonding system will ensure that the voltage difference between any 2 points is minimal. This minimizes the risk of electric shock if a person comes into contact with two different metal parts. The bonding system also facilitates the operation of overcurrent protection devices. By providing a low impedance path for fault current, the bonding system helps to ensure that a fault quickly escalates to a level that will trip a circuit breaker or blow a fuse. This helps to quickly de-energize the circuit and prevent further damage or injury. The NEC also provides detailed requirements for bonding. For example, NEC Section 250.92 requires bonding of service equipment enclosures, and Section 250.96 requires bonding of metal water piping systems. It's important to note that the bonding connections must be made using approved methods, such as bonding jumpers or bonding screws. These connections must be mechanically secure and provide a reliable electrical path. One common misconception is that grounding and bonding are the same thing. While they are both essential for electrical safety, they serve different purposes. Grounding provides a path for fault current to return to the source, while bonding ensures that all metallic parts are at the same potential. Think of it this way: grounding is like a highway for fault current, while bonding is like a network of side streets that connect all the metal parts together. To illustrate the importance of grounding and bonding, consider a scenario where a metal enclosure of an appliance becomes energized due to a faulty wire. If the enclosure is properly grounded, the fault current will flow through the grounding system back to the source, tripping a circuit breaker and de-energizing the circuit. This prevents anyone who touches the enclosure from receiving an electric shock. If the enclosure is not grounded, the fault current may not be high enough to trip a circuit breaker, and the enclosure could remain energized, posing a shock hazard. Now consider a scenario where two metal pipes are located near each other. If one of the pipes becomes energized due to a fault, and the pipes are not bonded together, there could be a significant voltage difference between the two pipes. If a person touches both pipes at the same time, they could receive an electric shock. However, if the pipes are properly bonded together, they will be at the same potential, and the person will not receive a shock. Another important aspect of grounding and bonding is surge protection. A properly grounded and bonded system can help to protect electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. When a voltage surge occurs, it can travel through the electrical system and damage sensitive electronic components. However, a properly grounded and bonded system can help to divert the surge to ground, protecting the equipment from damage. To ensure that a grounding and bonding system is effective, it's important to perform regular inspections and maintenance. This includes checking the condition of grounding electrodes, bonding jumpers, and other components of the system. It also includes testing the resistance of the grounding system to ensure that it is within acceptable limits. A high resistance in the grounding system can indicate a problem with the grounding connections, which could compromise the effectiveness of the system. The NEC provides guidance on testing grounding systems. For example, NEC Section 250.53 specifies requirements for testing the resistance of grounding electrodes. The resistance of a grounding electrode should not exceed 25 ohms. If the resistance is higher than this, it may be necessary to install additional grounding electrodes to improve the grounding system. In addition to the NEC, other standards and regulations may apply to grounding and bonding systems. For example, Underwriters Laboratories, or UL, publishes standards for electrical equipment, including grounding and bonding product. These standards help to ensure that electrical equipment is safe and reliable. It's also important to be aware of the potential hazards associated with improper grounding and bonding. Improper grounding can increase the risk of electric shock, fire, and equipment damage. It can also interfere with the operation of electronic equipment. Improper bonding can create voltage differences between metal parts, which can also increase the risk of electric shock. Therefore, it's essential to hire a qualified electrician to install and maintain grounding and bonding systems. A qualified electrician will have the knowledge and experience to ensure that the system is properly designed and installed, and that it meets all applicable codes and standards. The electrician will also be able to perform regular inspections and maintenance to ensure that the system remains effective. In summary, grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, while bonding ensures that all metallic parts are at the same potential. Both grounding and bonding help to prevent electric shock, fire, and equipment damage. To ensure that the grounding and bonding system is effective, it's important to comply with the NEC and other applicable standards, and to perform regular inspections and maintenance. Firstly, grounding and bonding are critical for preventing electrical shock hazards. Secondly, they help protect electrical equipment from damage due to faults and surges. Thirdly, adherence to NEC guidelines is paramount for safe and effective implementation. Fourthly, regular inspections and maintenance are necessary to ensure continued effectiveness. Fifthly, a qualified electrician should be consulted for installation and maintenance of these systems. Sixthly, understanding the distinction between grounding and bonding is crucial. Grounding directs fault current while bonding equalizes potential. Seventhly, the grounding electrode must be properly installed and maintained to provide a low resistance path to earth. Eighthly, all metal parts must be adequately bonded to minimize voltage differences. Ninthly, surge protection is enhanced by proper grounding and bonding. And tenthly, continuous learning and awareness of electrical safety practices are essential. Consider the application of grounding and bonding in a residential setting. The grounding electrode, typically a ground rod or a connection to the metal water pipe, is connected to the service equipment. The neutral conductor is bonded to the enclosure at the service entrance. Equipment grounding conductors run with the branch circuits to provide a ground path for appliances and other electrical equipment. All metal boxes and enclosures are bonded together to ensure that they are at the same potential. Ground fault circuit interrupters, or GFCIs, are installed in areas where there is a risk of exposure to water, such as bathrooms and kitchens. GFCIs monitor the current flow in a circuit and trip the circuit if there is a difference of 5 mA or more between the hot and neutral conductors. This helps to protect people from electric shock. In a commercial or industrial setting, the grounding and bonding requirements are even more stringent. Larger grounding electrodes may be required, and more extensive bonding systems may be necessary. Isolated ground systems may be used to protect sensitive electronic equipment from noise and interference. These systems use a separate grounding conductor that is isolated from the regular equipment grounding system. This helps to prevent noise from traveling through the grounding system and interfering with the operation of the equipment. It's important to note that grounding and bonding requirements can vary depending on the type of electrical system, the voltage level, and the location. It's always best to consult with a qualified electrician to determine the specific requirements for a particular application. The size of the grounding and bonding conductors is also critical. The NEC specifies the minimum size of these conductors based on the size of the circuit conductors or the service entrance conductors. Using undersized grounding and bonding conductors can compromise the effectiveness of the system. In addition to the physical components of the grounding and bonding system, it's also important to consider the overall design of the electrical system. The electrical system should be designed to minimize the risk of ground faults and to provide a clear path for fault current to flow back to the source. This includes using proper wiring methods, avoiding sharp bends in conductors, and ensuring that all connections are tight and secure. One common mistake is to rely solely on the neutral conductor for grounding. The neutral conductor is intended to carry the normal unbalanced current in a circuit, not to serve as a grounding conductor. Using the neutral conductor for grounding can create a shock hazard, as the neutral conductor can become energized if there is a fault in the system. Another common mistake is to neglect the bonding of metal water pipes. Metal water pipes can provide a good path to ground, but they must be properly bonded to the electrical system to ensure that they are at the same potential as other metal parts. This helps to prevent voltage differences that could cause electric shock. When working on electrical systems, it's important to always follow safe work practices. This includes de-energizing the circuit before working on it, using insulated tools, and wearing appropriate personal protective equipment such as gloves and safety glasses. It's also important to test the circuit to ensure that it is energized before starting work. In conclusion, grounding and bonding are essential for electrical safety. They help to prevent electric shock, fire, and equipment damage. By understanding the principles of grounding and bonding, and by following the requirements of the NEC and other applicable standards, we can create safer electrical systems for ourselves and for others. Always remember to consult with a qualified electrician for any electrical work and to prioritize safety above all else. The proper installation and maintenance of grounding and bonding systems are not just a matter of compliance, they are a matter of life safety. Regular inspections, testing, and adherence to best practices are essential to ensure the continued effectiveness of these systems and to protect people and property from the hazards of electricity. By investing in proper grounding and bonding, we invest in a safer future for everyone.